Hello. Uh, I continue to show no symptoms, and I continue to try to teach this wonderful class for all of you wonderful students. Today we're going to be talking about a topic which I have not actually talked about in class, which is the chi-square. Now, I have briefly mentioned its existence, but I have not actually done anything with it. We will be using a calculator. We'll also be using Excel. The Excel part I'm going to deal with that first, because in order to do a chi-square, we actually need to do a little bit of background math first. We'll use the calculator to do a little bit of it, but in reality, we need this. So let's go take a look over here. This section is what we're going to be talking about today. So today we're talking about the chi-square goodness of fit. Now, chi-square goodness of fit is one of two different chi-square tests, the other one being the chi-square test for independence. For a test of goodness of fit, what we're trying to determine is whether or not the data observed is what you would have expected. Now, the biggest issue with a goodness of fit is, of course, we have to know how many were expected. Now, a common tactic when it comes to goodness of fit is to assume that there is an equal number. This is frequently the case if we wanted to say determine whether or not there was a particular preference for one type of cookie versus another. In which case we might use a goodness of fit. The basic idea, though, of a chi-square is it's a little bit like a proportion test, except instead of just having one proportion, which being a yes or no, instead we can have multiple, as many as we want, realistically speaking, though you don't usually go much more than 4 or 5 in the real world. In this case, we're going to determine whether or not an eye color for a particular population happens to match the actual numbers. Now, this one right here are the probabilities for the actual eye color. I grabbed these off the internet, and they roughly add up to 1. Over here are the observed in our imaginary population. Now, in order to go ahead and perform a chi-square, we need to know what our expected is. Now, our expected would be the number of people we'd expect to have brown, given that 81% in this particular case happen to be brown, and same thing with blue, hazel, green. So for this, we need to know how many are in here total. Now, in an actual test, you would probably be given the totals already, but in the real world, you usually have to find these totals for yourself, so I'm going to do that for you. In Excel, we can actually use formulas, so I'm going to go ahead and tell it to give me the sum of all of these. I'm just literally going to type sum, select my tiles, and boom, it tells me my total number is 60. And to make each and every one of these, what I'm going to do is I'm going to take that number, which is 60, and I'm going to multiply it by the probability that I actually expected. In this case, 81%. And boom, there is my true expected value. Doing a little bit of magic here so I don't have to type this out every single time. I'm going to go ahead and boom. Here are the rest of my expecteds. Now you'll notice these are vastly different from the number that you actually see. Normally we're supposed to have 48 brown, but in the observed population we have 20. I mean, you probably don't even need to do a test to know that this is going to be different. But for the sake of argument, we're going to now perform a chi-square. And this is not a difficult task. First you pull up your calculator. We'll clear everything we see here because you don't need it. We'll click on Stat. We'll go to Tests. We'll then go all the way over here. It's one of the last ones. We have chi-square test and chi-square goodness of fit test. We're going to be doing the chi-square goodness of fit, or chi-square goth. Notice I'm calling this a chi, because that is a Greek letter chi, not an X. So just keep that in mind. This is a chi-square test. Press enter, and it then asks me to know where my observed and my expected are. And here's my first problem. I need to put my observed and expected in here. Not a difficult task. We go to Edit, and what we're going to do is we're going to replace all of these numbers. You'll notice I have not actually deleted the numbers from the previous tests we had done, I did yesterday. But I'm going to replace these with my observed, which I'll put in my first column. So 20, 12, 12, and 16. And for my expected, I'll put them in here. 48.6, sorry, not 0.6, but 6, 3.6, and 1.8. and these are the numbers that would be expected, assuming that it fit a normal population as measured in the real world. So now we go into stat. Now we can finally get to our chi-square goodness of fit. And we have L1 for observed, L2 for expected, and then we get this degrees of freedom. Now, degrees of freedom for chi-square is not done the same way as it is done with pretty much anything else. With all of the things we've done so far, it's been n minus the number of parameters. Here, degrees of freedom is still an n, but it's not the number of people, that'd be 60. Instead, it's going to be the number of categories. And over here, you'll notice we have 4 categories: brown, blue, hazel, green. And it's going to be the number of categories minus 1. So if we have 4 categories, then minus 1 of those would be 3. And this, once again, it comes down to the true definition of degrees of freedom, which is how many of these can vary freely without anything affecting it. But don't worry too much. The main thing to understand is it's the number of categories minus 1. So if we had 10 categories, we would subtract 1, making it we would 9 degrees of freedom. And if it was like 5 categories, it'd be 4 degrees of freedom. Enter. And here's my chi-square. Now, that is a huge number because, as we said before, I mean, these are vastly different. They're clearly not the same. And my probability is basically 0. 2 times 10 to the negative 33, that's basically 0. So ultimately, we know for a fact that this is probably a vastly different number. That's pretty much all you need to know for chi-square goodness of fit. Just keep in mind that you have to first calculate your expected if you're not given the expected to calculate them, which is usually based on something you'll be told in advance. In the case of eye color, it's the probability of each eye color. You might be told instead, assume that they are all the same, in which case you would just make sure that each category in the expected is literally the same. Go ahead, build your two-way table with those observed and expected. Put them into your lists. Finally, run the goodness of fit test with the number of degrees of freedom equaling the number of categories minus 1. That is all for this video, and I hope you have a wonderful day.